Okay, so previous lecture we looked at flow visualization and we looked at three different types: a path line, a streak line and a streamline. And in a steady flow they all do the same thing, and in an unsteady flow a streamline has no meaning, and a path line and a streak line will generate different pictures with the same flow. So you need to be aware of what you're looking at if you're seeing a picture of an unsteady flow to work out what's going on with the fluid. And stream tubes are very useful for us. So these are collections of streamlines that bound, if you like, a virtual tube, and because of the property of a streamline that it's tangential to the flow direction all the way along it, effectively a stream tube is like a virtual pipe of fluid. So the same amount of mass that goes into a stream tube comes out the stream tube at the other end, and we can look at how stream tubes get wider and narrower, and these can tell you where the flow speeds up and where it slows down. So what we're going to look at today is we're going to look at conserving force and energy along stream tube. And these are two equations called the Euler Equation and the Bernoulli Equation. And the Bernoulli Equation is particularly useful for us because it allows us to generate a pressure distribution in a flowing flow. And one of the important things to be aware of in the Bernoulli Equation is it comes with some assumptions and characteristics, and you need to be aware of these so you apply the Bernoulli equation correctly. Okay, so our kind of test box or test problem is this. So we've got a box and we've got a uniform flow on the right hand side coming in, and we've got a uniform flow of the fluid leaving the right hand side of this box, and the grey stuff is the fluid, and we've got some objects, some random objects in the volume, and the flow is going to have to go around these objects to get from the left hand side to the right hand side. And we're going to make some assumptions. We're going to assume it's an incompressible fluid and it's inviscid. So that's a fluid with no viscosity, and what that means is the no slip boundary at a wall does not apply. So we can have a flow velocity at the wall. Okay, this is one of the key assumptions about the Bernoulli and the Euler equation. Okay, so just conceptually what's going to happen? Well, so you're going to have an element of fluid, it's going to come in here and it's got to get through some narrow gaps, so it's probably going to speed up, and then it's probably going to slow down, and then it's going to speed up again. And there must be some forces that are making this fluid speed up and slow down. We want to work out what these forces are and how they are conserved, and how we get around working out force distributions in fluids. Okay, so let's imagine we have solved the flow field, and if we've solved the flow field, we can do a stream tube plot. So all of these lines are boundaries of stream tubes, and so you can see on the left hand side here they're all equally spaced, and what I'm assuming here is each one of these is the white spaces are stream tubes, and I've got an equal amount of mass going down each of these stream tubes because it's a uniform velocity profile, and these things are equally spaced. Okay, so if we pick one of these stream tubes, so let's pick this one. We've got stream tube comes along here, so it comes along here, and then at this region the stream tube is getting very narrow. So what we know from the previous lecture is that the flow is speeding up in this point, and then we see that the stream tube gets a bit fatter, so the flow slows down here, and then it gets thinner again, so it's speeding up through here, slows down, speeds up a lot through here, very narrow region, and then it slows down quite quickly, and returns to its original velocity here. which is pretty much the same as the velocity here. Okay, so that's what's going on, and the question is, well, why is that going on, and how can we understand this? How can we do some calculations to make sure to do this prediction and to work out how much fluids are going to be speeding up and slowing down? So this is another example of the flow field. So instead of looking at the velocity field, the velocity vectors if you like, what we've done here is we've taken the dot product of the velocity vector with itself, taken the square root. That gives me the speed, or the velocity magnitude. Okay, and we can see out here we have fairly low speed flows, very low speed flow here, and the sort of the hotter regions, so the yellow regions here and this region here, we can see there are high speed regions of the flow. So if we have a fluid element, starts off here very slow, speeds up, gets to the fastest point here, then it starts slowing down, and it speeds up here and it slows down again, speeds up here and then slows down again. Okay, so something must be making this fluid do this. So effectively what we're going to do is we're going to do a force balance on a fluid element that is, if you can imagine a sort of a small cylindrical section of one of these stream tubes. So we could choose any small section, and then we are going to do a force balance on that flow element. And the force balance comes from Newton's second law. Force is equal to mass times acceleration. So we've got mass times acceleration here, and that must be equal to the forces acting on this fluid element, and that's due to the pressure gradient along the region of the flow and the gravitational force that's acting on this element. Okay, and this is a steady state flow. So if we do a force balance on this this hypothetical fluid element, then these forces must balance, and nothing is changing. So this equation must hold. Okay, so next slide we go through and work out what this force balance must be. So what we're doing here is here's my stream tube, and I could have chosen any of those stream tubes that I showed you in the previous slide, and I choose my little flow element, or my little fluid element here. So it's a small volume, so I'm using these small deltas to mean a small length here, and this is a small area, and then I think about what the forces are, and I discretize my forces onto this particular force element. Okay, so I've got a coordinate direction. So this is my positive S direction, if you like. So you can think of this as the X direction, if you wish. And we start thinking about what are the forces going to be acting on this particular lump of fluid. So the first one is the acceleration. So we know the acceleration is the rate of change of velocity with distance, and I apply the chain rule to this. So I say that that's the same as du by ds and ds by dt, and then I know that ds by dt is the velocity, so I can write that the acceleration, or the rate of change of velocity with distance, is the same as the velocity multiplied by the rate of change of velocity with distance along this coordinate line. Okay, and I've said the length of my fluid element is ds, and the cross-sectional area is dA, and so I can define my volume of fluid as ds by dA, and I can say that the weight of the fluid is the mass times gravity, and the mass is the density times the volume, and this force is acting in the z direction. So this is, if that's the z direction up, then my gravity vector is going to be acting in this direction, and I'm doing a force balance, remember, in the s direction. So I would need the weight acting in the z direction, I need the component of that acting in the s direction, and I work that out by taking cos theta. So cos theta is effectively the angle between the hypotenuse ds and the angle of the actual force. So this we define as theta, and this gives me the component of the gravity force acting in the s direction. And then we start thinking about the pressure forces. So there's going to be a pressure force if F1, which is acting in this direction, and F2, which is acting on the other surface, are different. If F1 and F2 are the same, there's no net pressure force. Okay, so let's say we know what the pressure is at S equals 0. So that's on this face here. And we know what the pressure is, and we know what the area is, so we know what the force is. That's just the pressure times the area. And then we don't know what the pressure is at this point, but let's say we know what the pressure is here and the pressure gradient along the s direction. So we can make an approximation of what this is using a Taylor series, and this is pretty good as long as ds is really small. So this thing in the brackets here, this is my pressure at the 2 location, the upstream face, and this is my area. So this thing together is the force that's acting on this face at position 2. Okay, so we've got all our forces. So now what we need to do is build our force balance that must hold, because it's steady state and all my forces are in balance. So I've got mass times acceleration, so I've got density times the volume, and then I've got my acceleration. So I've said that this is us dus by ds, so that's what this bit is here. And then I've got my force, my net force, and my net force is effectively these two added together. So I've got PdA here, so this is F1, and F1 is acting in the same direction as my positive s-axis, so this is positive, and this thing here, the bracket multiplied by dA, this is F2, and F2 is acting in the opposite direction to the s coordinate, so therefore I put a negative sign here, and then effectively I'm after the net force from this. And as you can see from this, the PdA here and the PdA here cancel. So this term here, this is my net force. It's just due to the pressure gradient. It doesn't, the actual pressure makes no difference. Okay, and I've got the weight of the fluid. So I said the component of my weight acting in the s direction is the cos theta. And as we can see from my sketch, this means my force is acting in this direction. And this is the opposite sign to the positive s direction. So I'm putting a negative sign here. So here's my sort of force balance. Okay, so this is my force balance that must hold. So what we need to do now is clean it up a little bit and make it a little bit more useful. Okay, so here's my equation from the previous slide. Haven't done anything to it here. So what I do is I do two things. The first thing I do is I divide everything by the volume. So I divide this thing by the volume, divide this thing by the volume, this thing by the volume, this thing by the volume. And the second thing I do is I replace cos theta with its definition, which is dz by ds, so I can replace that there. And then what I do, the third thing I do is I take the limit. So what I'm doing here is I'm shrinking this infinitesimal control volume down to a point, and when I do that, all of my infinitesimal terms turn into differential point quantities. Okay, and so we end up with a force balance that looks like this. So what we've got here is we've got an inertial term. So this is a force due to the density of the fluid and the velocity of the fluid. So if you think about the amount of force in a ping pong ball and golf ball, they have a different inertia, okay? Even if they're traveling at the same speed, they have a different inertia. So this is your inertial force. We've got the pressure gradient. So the pressure gradient creates a force, and it's the pressure gradient that actually makes the fluid move from one end of a typical flow to another end typical flow. And then we've got a change in force due to the fluid moving against gravity. Okay, and this is called the Euler equation, and the interesting thing is that it says that the sum of all these forces is 0. Okay, so let's flick back a couple of slides back to here. So what my Euler equation says is, if I choose a fluid element here, I say effectively there is 0 force here. Okay, and as I go along here, there's still 0 total force at all points along this streamline, but the forces can change form. So for instance, in this region the flow is speeding up, so something must change because the liquid has more inertia here, and what we find is the local pressure goes down. Okay, so the pressure gradient, if you like, has a negative sign, and the local pressure goes down. And then when we get to this point, the high speed region, so there's lots of inertia here, so then we move into this region, and the flow is slowing down, so its inertial force is reducing, so the pressure gradient changes sign, and the pressure has to go up. Okay, and it keeps doing this, so it goes along here, it has to accelerate here, so you have lots of inertia force, but low pressure, and then the flow slows down, the pressure recovers. So pressure changes in a moving fluid, and it responds to its inertia. So we've assumed that this is an inviscid fluid, but this effect also happens in viscous flows. But this equation ignores viscous forces, and so it's a reasonable assumption away from a wall. It's definitely not a good assumption in a boundary layer or in a viscous flow near a wall. Okay, so that's the force balance. Now we can also do an energy balance, because we know that energy is equal to force times distance. So if I take my force equation and I integrate it with respect to S, then I end up with an energy equation. If I go from a force equation, I integrate it with respect to distance, I end up with an energy equation. So I take each of these terms and I integrate with respect to S. So let's take dP by ds, and effectively what I do is I say I want the integral of dP by ds by ds. So the two ds's cancel, and I end up with an integral of dP, which ends up being p plus an integration constant. And I do the same for dz by ds, and I also do the same for this inertial term. And there's a little bit of a step here, so we can write this term as density d by ds of u squared over 2. If you take d by ds of u squared over 2 and you differentiate it, you end up with this. Okay, so these are two forms of the same term effectively. And so if you take the integral of d by ds u squared over 2 ds, you end up with this term here. Okay, and this is the Bernoulli equation, and you'll probably be using this much more than the Euler equation, because this is a way to work out the pressure distribution in a moving fluid. And we've got three terms here. So we've got a kinetic energy term, we've got a pressure energy term. So here pressure represents stored energy, if you like, and we've got a potential energy term, and we recognize this from hydrostatics. And interestingly, this thing is a constant. So let's say, for instance, let's forget about potential energy. Let's say we've got a horizontal streamline and Z doesn't change along my streamline. So we can neglect this. And let's say my streamline starts off in a region in a large tank where the velocity is really small. And then my streamline goes into a pipe. So the left-hand side of the equation will be the pressure in the pipe and the local kinetic energy, and the right-hand side will effectively be the pressure in the tank, because there's no velocity. And this pressure at no velocity is called the stagnation pressure, and it's quite important because effectively it tells you how much stored energy that you've got in your fluid. So if you think about a pressurized tank and that's connected to a pipe, the amount of flow or kinetic energy that you can transfer to your pipe is a function of the pressure you've got in your tank. Okay, so key thing for the lecture is you need to know how and when to apply the Bernoulli equation. So you get the Bernoulli equation in your list of equations, so you don't need to remember it, but you do need to remember how to apply it. And the key thing to remember is we used a streamline to do this force and energy balance, and there are some assumptions associated with streamlines. The first one is that the flow is steady. Otherwise, streamlines don't mean anything, they're just nonsense. There's no viscous forces, so this is not true in real life, but it's not too bad an approximation away from a wall. And we've also assumed that the fluid is incompressible, and this is an assumption that we're making in part one. It's not generally, doesn't have to be true, but in part one this is very much an assumption. Okay, so when you apply the Bernoulli equation, you've really got to make sure that these things are all true, and if you can make sure that that's the case, then you can apply the Bernoulli equation, you can work out the pressure distribution in the fluid, which is very handy. So this gives you a quick example of a real-life example of how pressure changes in a fluid can cause observable changes. So imagine out here we've got a tank, a big tank, and it's pressurized, and it's so big that there's negligible flow velocity there. So this P0, this is your stagnation pressure in the tank, and that's what we've got here. And then we draw a streamline through a nozzle, goes into another big tank. So what we're interested in is what's going on here at station number 1. So we know from the Bernoulli equation that so we can imagine that as the fluid moves along this streamline, it's getting it's going through a narrower and a narrower gap, so it's going to speed up. So the kinetic energy of the fluid is going to increase, and since the stagnation pressure has to stay the same from the origin of the streamline, if the kinetic energy is going up, it means that the local pressure is decreasing. So as the flow speeds up, the local pressure goes down and down and down, and it can get to sort of a critical point. So in real fluids and real liquids, the local pressure mustn't exceed reduce less than the vapor pressure. So the vapor pressure is a pressure at which the liquid boils. So this is a physical constant, a bit like density and viscosity and thermal conductivity, and it's a very strong function of temperature. So as you increase the temperature, the vapor pressure rises, and for instance, when in water, when you heat the water to 100 degrees C, the vapor pressure equals local atmospheric pressure, and the liquid boils. So this is something you can try at home. So you can also do this. So you can also make the liquid boil by reducing the local pressure in the liquid to the vapor pressure. And this is what happens when flows cavitate, and you saw this in the first lab when you started the module. So what's happening here is you start off at the stagnation pressure of the tank, and as the flow accelerates, the local pressure reduces and it reduces and it reduces, and if you reduce it enough, which means effectively you try and pump more and more fluid, so it's going faster and faster through this narrow throat, then the local pressure at the throat will equal the local fluid vapor pressure, and the liquid will boil. So effectively you get bubbles starting to appear in the fluid, and then these bubbles start going downstream, and then when the flow recovers, so the pressure in the fluid recovers because the flow is slowing down, these cavitation bubbles disappear again. Okay, so this is a nice example of the local pressure in a fluid and how the local flow speed can create changes in the local pressure of the fluid. And this is parameterized by something called the cavitation number. So we take the pressure difference and divide it by the kinetic energy, local kinetic energy, and clearly if you want your flow not to cavitate, this cavitation number must be bigger than 0. And if it reaches 0 or gets anywhere near it, you're in trouble, and you're going to start producing problems in your equipment. Okay, so we covered quite a lot here. We used a stream tube, we did a force balance, we ended up working out an Euler equation, and then we integrated along that Euler equation to work out an energy balance equation called the Bernoulli equation, and we showed that the total mechanical energy, so there's no thermal energy here, is the sum of 3 energy forms: kinetic, potential and pressure energy. And although these 3 things can vary along the streamline, the sum of these must always be the same, and the sum of these is defined by the stagnation pressure. And really important, we need to make sure that the Bernoulli equation assumptions hold, and that's because we are using a streamline to work it out. So the first assumption is it's steady, second assumption is no viscous forces, and the third one we use in part 1 is that it's incompressible. And cavitation is a nice example of how the local pressure can vary and create changes in the fluid, something you can see very easily. Okay, thanks very much.